Hello dear friends, let's solve this paper winter 17 component 4-2. Yeah, the paper is paper 4 of A level physics, ASN A level, October November year 2017, and then component 4-2. Okay, let's get into the first question. So the first question is state Newton's law of gravitation. We know that Newton's law of gravitation. So this has 2 marks, so we have to give 2 point. What is the 2 point? First, maybe you can try to give the equation, or we can state it in the words about the force and about the distance. So 2 points. So the force between the 2 point masses is proportional to the product of their masses. This we know because F directly proportional to m1 and m2, and it is also inversely proportional to the distance between them, the square of the distance between them, or the separation distance square. So how we can make an answer is the force between 2 point masses is proportional to the product of their masses and inversely proportional to the square of their separation. So 2 marks. Let's look at the question B. Okay, what we have here is a planet Jupiter, and there is a satellite, and this satellite is orbiting Jupiter in a circle, a perfect circle. Obviously this is not a practical situation, but why this is perfect, given as a perfect circle, is for a reason. So one of the moon Io may be considered to be uniform spheres. So this uniform sphere is a keyword here, and isolated in space means there is no resultant force because of any other mass surrounded by, and then no external forces acting on. Now what are the information we can have here? For example, the density of the Jupiter is given, and the radius of the planet Jupiter is given, and the radius which the moon Io orbits is the multiple of the radius. That multiple is n. So we have Jupiter and its mean density rho, and then radius capital R, and then we have Jupiter's moon, a mass small m, and radius of orbit is nr, so multiple of r. Okay, so this we have to remember because this is a key information we need to use for the next question. Now what they are asking is, so that the time t, capital T, is related to the mean density rho of the Jupiter by this expression. Now we understood that density is not a usual information that we will be dealing with gravity and then this sort of problems. But if you wonder why it is given, I'll explain in a minute why it is given. For example, for this question, first what we have to do, we have to understand the forces acting on the moon. So why moon is in orbit? Because the gravity is pulling the moon, and the moon is going in a circular manner. So what is the force associated with circular manner? Is centripetal force. So unless until this centripetal force is equal to the gravitational force, the moon will be not staying in the orbit. So this is our first step. So force due to gravity is equal to force due to centripetal force. Okay. Now let's write the expression for these two forces. For example, force due to gravity is capital G, mj means mass of the Jupiter, and mio means mass of the moon, and then it's n square r square, because in general this force of gravity, as we stated in the first question, is directly proportional to capital M small m and inversely proportional to the distance between them. Now the distance between them is nr, so the square of distance between them is n square r square, and the centripetal force is that we know already, so mv square by r. So what is the mass here? Mass of the moon, so mio, and then velocity v square. Now this is velocity, this is also we have to pay attention little. This is velocity, and the distance from the Jupiter to the moon, what we call it as a radius, is nr. Okay. Now we are equating both these equations, and we try to eliminate all the things possible in the beginning, so we don't want to have complication in the end. For example, mass of the moon in both sides we can cancel out, and then this side we have n square r square, this side we have nr, so that thing we can cancel. So if we cancel out, what we have here is capital G divided by small n mass of the Jupiter equal to the velocity square. Now the problem is we do not know what is the mass of Jupiter, and we also do not know the velocity square, what is velocity. So can we, if we look at the question again, is there anything that we can relate, or we can use it to find the mass of the Jupiter? That's where it's given. One, it's uniform sphere. Two, the density. So in general, what is density? Is mass by volume. So from here, can we get mass? Yes, of course. So mass is nothing but, density is nothing but mass by volume. So what is mass? Density multiplied by volume. This is a perfect sphere we are talking about. So the volume of a sphere is 4 by 3 pi r cube, and the density is rho. So mass is, using mass equal to volume multiplied by density, we are getting mass of the Jupiter. And then what about this V? So V is velocity. But what is V when something is going in circular? V is distance by time. Okay. So what is the distance here? Is the circumference. That's how much it travels divided by the time it takes. The time it takes is t. Okay. So what we have here, 2 pi, the circumference of a circle is 2 pi r. Here in this case radius is nr. So it's 2 pi nr divided by t. Now let's take this equation G n m j, mass of Jupiter, equal to velocity square, and replace what are the informations that we had new. What we will have, so instead of mj I am going to put 4 by 3 pi r cube rho, and instead of v I am going to put 2 pi nr divided by t. So if I replace everything here, so mj is mj, but v we define as 2 pi nr divided by t. So what we have here is v square. So we have to square everything. So what we get, 2 square pi square n square r square divided by t square. Now so we'll cancel out what are the things equal. So obviously from here 2 square we can cancel the 4. Instead of so pi square we have, so we can cancel the pi. 1 pi will be remaining this side, only square gets cancelled out. R cube is here, r square is this side. So we can cancel out the r square, that side, left hand side 1 r will be remaining, and density we cannot cancel. Similarly t square we cannot cancel. So if I rearrange this equation, from t square from right hand side I can move it to the left hand side, so it will go as multiply. So and it will be what the relationship we asked, rho and t square should be there. So I kept the rho and t square left hand side, bring the g divided by n to the right hand side, so it will come as a n divided by g. So what I have here, n3 in the denominator, okay, and then this side what I have here, if I move that, 3 pi n cube divided by g. That's exactly the relationship they asked us to prove. Done. Nice job. Yes, okay, let's move to the next question in the next page. So what they are asking here is, the radius r of the Jupiter is 7.15 multiplied by 10 power 4 kilometer, and the distance between the centers of Jupiter and Io is 4.32 into 10 power 5 kilometer, and the period time t, capital T, what it does mean, how long it take to complete one orbit, one circle. Okay, and from the previous relationship we can take this equation, and from here what they are asking, calculate the mean density rho of the Jupiter. So we will keep only the rho here, we will bring the t square to the right hand side. So what we will have, rho equal to 3 pi n cube divided by gt square. But problem here is we do not know what is n. That's why this crucial information is given. Distance between the center of Jupiter and Io is 4.32 into 10 power 5 kilometer. Okay, so this distance is equal to nr. If you refer the picture, that's exactly the radius nr. So nr equal to 4.32 into 10 power 5 kilometer, and r is also given. R is radius of the Jupiter is 7.15. So if I replace r, what is n? Simply 4.32 divided by 7.15 into 10 power 4 kilometer. Okay, so n is a number, it does not has any unit, so it's 6.0419. Now if I replace all the values here in the equation, first equation, rho equal to 3 pi n cube divided by gt square. G is a gravitational constant. I get this equation, but what we have to be careful about is the t time period is given in 442.5 hours. So we have to convert into standard SI unit, which means we have to get it into second. So what I am going to do is multiply it by 60 and multiply by another 60. So I'll multiply by minutes and then I multiply by seconds. So what I get is 1,53,000 seconds. Okay, this we have to be very careful, because if we don't convert this into second, then we will not get the final answer. So if I do the calculation and then using calculator, what I get is 1.33 times 10 power 3 kilogram meter power minus 3. Okay, now this is the density. Obviously the units are matching, so we'll write the answer 1.33 into 10 power 3. Yeah, bravo. Okay, let's look at the next question. The Earth has a mean density of 5.5 into 10 power 3 kilogram meter power minus 3. It said the planet be made of rock. So what is the information we are getting here? The rock, some planet made up of rocks density is 5.5 into 10 power 3. By reference to your answer 1, comment on the possible composition of Jupiter. So what we have to do, we have to refer this answer 1.33 into 10 power 3 kilogram meter power minus 3 to the Earth's density. So there is small logic here, just small logic. If Earth's density is made up of rock, we have the Jupiter's density relatively less than its density. So the material making Jupiter should be less denser than the Earth. So what is less denser than rock? So obviously rock is a solid, so something like fluid we are talking about, liquid or gas. Okay, so how we can write? We are comparing the result. Jupiter is less denser than the Earth, so it could be made up of materials like gas or liquid, which is less denser than rock. Yeah, that's all. Very easy. Yeah, okay. We'll say sayonara to this question. We'll move to the second question. State what is mean by specific latent heat. So this first we have to have the idea what is mean by specific heat. Specific heat is the amount of energy required to increase a substance by 1 degree. Now what is specific latent heat is the quantity of thermal energy required to change the state of, initially it was increase the temperature by 1 degree. The latent heat is changing the state of unit mass without changing the temperature. For example, how you will change ice cube into liquid without changing the temperature. We will keep on slowly increasing the temperature, but the temperature of the ice cube will not be increasing because the temperature is used to melt the ice cube. Okay, so how we can write? Specific latent heat is the quantity of thermal energy required to change the state of unit mass without changing the temperature. Yep. Okay, let's look at the B question. A beaker of boiling water is placed on the pan of balance as illustrated in figure 2.1. Let's look at the figure. What are the informations we have? We have a heater, we have a balance pan, we have boiling water, we have a variable resistor, and we have a power supply. There is ammeter and voltmeter. So without reading further, let's just look at what are the quantities they can measure here. For example, they can measure how much current is flowing and what is the voltage across the heater. And also there is a balance pan, so we can measure the mass. I was initially wondering why there is no thermometer, but we are yet to find. Okay, now the water is maintained at its boiling point. Okay, so no need thermometer. So it says it's boiling point. We know that water's boiling point is 100 degrees Celsius, whatever. Now there is a change occurring, because why it is occurring? So if you heat the water above the boiling point, the temperature will not increase. Simply the thermal energy that you supply will be used to vaporize the water, meaning that there is a phase change. Phase change is happening. Okay, and the results are shown here. What is the result shown here? Reading of the voltmeter and ammeter. Now, the question they are asking, energy is supplied continuously by the heater after boiling point. State where in this experiment external work is done. Until boiling point, whatever the work is being done is internal work, because the temperature is not going to the surrounding. But now, once after the boiling point, the energy we supply is actually going to the surrounding by means of vaporization. So this vaporization or vaporized gas will go where they will go? Atmosphere. So where external work is done is in the atmosphere. External work is done against the atmosphere. That's all. Now the second question. Internal energy increases. Explain your answer. Okay, so obviously we are supplying energy inside, but we have to prove or tell how internal energy increase. For example, first water evaporates from liquid to vapor because internal energy increases, or the molecule's potential energy is increasing, or the internal energy is transferred to the surrounding because it's increasing. If it is decreasing, do you think it will be able to surround, give the energy to the surrounding? No. So these are the things we can write it as a point. 3.3 mark. Also I refer a marking scheme. So I'm sure that these three are 3 points. Okay, let's move to the next question. Use data in figure 2.2 to determine the specific latent heat of vaporization of water. Okay, by the way, specific latent heat of vaporization means how much energy it took to move from liquid phase to gas phase. That's what vaporization. If it moves from solid to liquid, then it's melting. If it move from solid to gas, then it's sublimation. Yes. Now, okay, let's see the figure 2.2. We have voltmeter reading and we have ammeter reading, and we have change in we have mass balance reading. Okay. So what is the equation we have to use it here? Change in thermal energy is mass multiplied by specific latent heat. So this is the equation that we know. Now what is delta Q here? It's change in power into time. In general, what is energy? Power multiplied by time. So what is change in energy? Change in power multiplied by time. That's all. So in the delta Q equal to m LV, we know that m is change in mass and LV is latent heat of vaporization. Okay. Now let's rewrite this equation, because we are bothered by LV. What is LV? Okay. Can we rewrite this equation? From this equation we found that LV is delta Q by m. Now we can replace this delta Q as power into time, delta P by time by m. I have done nothing extra. But problem is, now we have to know what is power. Power is energy by time. Change in power is change in energy by time. Now what energy is changing here? The delta P is actually electrical power loss. I mean, why power loss? Because we are supplying electrical power. Okay. The power loss from the heater is actually the power gain for the water. That's why we are interested in this. Now how we can calculate? So this power loss is actually initial power, final power minus initial power, as simple as it is. Yeah, okay. Now how do we measure electrical power? It's simply voltage multiplied by current. Now let's put all these things in the equation. Instead of delta P, we will put V final, initial final power minus initial power. So V final multiplied by I final minus V initial minus multiplied by I initial times T, and how much mass has changed is M2 minus M1. Okay, so let's simply substitute all the values here. The answer we get is 2274, 2027, 2274.146 joule gram inverse. So the unit is given, all we have to write is just number. Nice, 8 out of 8. Okay, let's move to the next question. Okay, nice question. Define the radian. So before defining the radian, first we have to understand what is radian itself. Okay, so let's look at this animation. First, let's wonder what is angle. Angle is nothing but how much one ray is above the other ray. That simply is angle. But problem with angle or degree is this degree does not care whatever the length of these lines. Okay, even if they are infinite line, the angle is same. So that's why we need radian. Okay, now let's see what is radian. In general, angle is arc length divided by radius. Let's assume we have a circle of radius r. Okay, unlike that the previous case, we don't bother about how much the one line length or another line. Let's assume this. I'm going to take a segment of arc length same as radius of r. Okay, what do we see here is red color is radius. So I took the same distance in the arc length also. Now there will be some angle, right? It will make some angle. This angle is 1 radian. Okay, let's put these things in our question. What is radian? Angle subtended in the center of a circle where arc length is equal to radius. This is the key point. Arc length is equal to the radius. Okay, now let's move to the second question. State by reference to simple harmonic motion what is meant by angular frequency. This is a very simple and straightforward question. What is frequency is 1 by time, 1 by time taken. What is angular frequency? It's 2 pi by time. That's all. By the way, why it is 2 pi, I'll make another video. Okay, it's a nice, interesting topic. Yes, we can move to next question. Okay, a thin metal strip clamped horizontally at one end has load of mass m, capital M, attached to its free end. So what we are making here is we are fixing a lever in the wall, and then on the other end there is load mass. So out of curiosity, if we touch the mass, then it will oscillate up and down. Okay, obviously the initial force is given by our finger, but why it is oscillating in the horizontal is because of gravity. So we know that gravity is involved, and the force we give involved, and it also depend on tension of the rod, flexibility of the rod, everything, and also how much it swipes, what is the length it swipes, it depend on the length of the rod. Okay, so these are the information that we can get from this picture. Now let's see what is the question that they are asking. So they have given an equation here, A equal to minus C divided by m L cube x, where L is effective length of the metal strip and C is the positive constant. Nice. Explain how the expression shows that the load is undergoing simple harmonic motion. Now we don't need to bother by the image now as of now, but simply by looking at this expression, actually we can tell how we managed to tell y equal to mx plus c means straight line. Looking at this equation, we can tell how, because one is proportional to other. Okay, in this case A is proportional to x. Okay, which means amplitude is proportional to the distance it move. Okay, and the minus symbol is important here. Okay, so this acceleration is proportional to the displacement in opposite direction. Okay, that's one point. Second is if we have to remove the proportionality, then we obviously have to introduce a constant, right? What is that constant? C divided by m L cube. How do I know this is a constant? C is a constant, they already given. Mass of the box or piece, whatever it's not going to change, so it is also a constant. L is length of the rod is also not going to change, so it's a constant. So this is proportional to minus x by this constant C divided by m L cube. So A equal to C divided by m L cube minus x. Voila, simple harmonic motion. Yes, let's look at the next question. For a metal strip of length L equal to 65 centimeter and a load of mass m equal to 240 gram, The frequency of the oscillation is 3.2 hertz. So now we have length and mass information. Okay, and frequency also. Calculate the constancy. What we have to do? Simply, we have to do anything. Okay, sorry, we don't have to do anything. Simply, we just put these things in the formula. The formula is also given in the front page. Okay, let's see. But problem here is, what is x? Okay, do we have anything that can relate x given here? And what is acceleration? Is there any information provided about the acceleration? Okay, that's the idea. Now we know that this formula, acceleration is minus omega square x. Then we have, from this we can get omega square is acceleration by minus x. Okay, but what is omega? Omega is 2 pi f. That's what we define angular frequency. Okay, if omega is 2 pi f, then omega square is 4 pi square f square. Okay, let's put things instead of acceleration, let's put this guy. Okay, 4 pi square f square. Okay, now if you look at this, what I have done, the first equation is, I have rewrite the equation as a divided by minus x equal to c divided by ml cube. Instead of a divided by minus x, I have put omega square. That's all. Okay, from here what do we want? The constant c. So I'm going to rewrite this equation for c, making the c as a subject. 4 pi square f square ml cube. All the information we have, just replace it. But what we have to do, mass is given in gram, so SI unit we have to change it into kilogram. Also length is given in centimeter, that we have to convert into meter. If we do the calculation, then what we get is 26.64 kilogram meter cube second inverse, second power minus 2. This is a C. Write the answer and then we can go for next question. As simple as it is. Okay. Now actually people think that theoretical question is easy, problem solving question is difficult, but actually it's the vice versa. It's the opposite actually. Because problem solving question, we do know what is a marking scheme and we will not skip any point. But in theory question, in complete theory, writing in words, we will be not sure that what are the points awarded marks and what are the points not doesn't award marks. Okay. Now, so actually I was trying to make animation how ultrasound work, but that will deviate this purpose of solving paper. We just want to focus on solving paper. That we will, the animation I'll attach into the lecture and then I will add the same question again. Yes. Now, what's the core principle? We have a piezoelectric crystal inside and then we will supply the voltage across the piezoelectric crystal, so it will vibrate. Now, if we supply the voltage enough to make the vibration which matches with the natural frequency of the crystal, then it will resonate. Okay. Now, we do understand that how much potential we have supplied. So, we can also see what is the frequency it will resonate. This piezoelectric crystal can do the reverse effect also. Means if it receive the vibrations or oscillations, then it will produce potential difference across the crystal. So we can see the reflected ultrasound also. This is how basically it works. So if we can write point by point, we get all this point. One piezoelectric crystal is used as a transducer. This is a marking scheme word, transducer. And there is potential difference across the crystal to make distort, move in one axis, shrink in one axis and then expand in another axis. This potential difference causes the crystal to vibrate. Okay, we discussed. When the applied frequency is the natural frequency of the crystal, then it resonates. Since the natural frequency of the crystal is ultrasound, it emits ultrasound radiation. This is very, very important point because the system itself is called ultrasound scanning. Okay. The crystal also creates potential difference when it receives the reflected ultrasound back. Okay. Now the reflection wave is maybe you can write a program for it to analyze the intensity, and then the intensity of the reflection depend on the tissue thickness and the type. So you can distinguish various types of tissues. So you can just map which tissue is there, and then you can create an image. Okay, yes. Now let's move to the next question. Ultra frequencies, okay, what they are using is as high as 10 megahertz are used in medical diagnosis. Suggest one advantage of the use of high frequency ultrasound rather than lower frequency ultrasound. Okay, they are simply asking why they are using higher frequency, not lower frequency. We know that lower frequency can travel long distance, okay, but it will give poor resolution. Why? For example, you can compare why the sky is blue in the afternoon and why the sky is red in the evening. Because blue scatters fast. Okay, red goes for long distance but scatter very less. This is the same reason. So lower frequencies can penetrate more but give poor resolution. High frequency can penetrate less but give nice resolution. Human body is about maybe 30 to 45 centimeter in any direction. So we actually not bothered by how long it can penetrate. We want the information, detailed information. So we prefer higher frequencies. So how we can write answer? Lower frequencies cannot penetrate more depth, but this is this reasoning. The marking scheme is higher frequencies penetrate less depth but give higher resolution. This is the answer. So small tissues or structures can be resolved. Yep. Okay, let's go to the next question. The analog signal from a microphone is to be transmitted into digital form. Okay, what we are discussing here is analog digital converter in figure 5.1. Okay, let's see the figure 5.1. Okay, it's a nice signal. In x-axis, time is given from 0 to 1.2 milliseconds, and in y-axis we have microphone output in millivolt. Okay, now what is the question that they are asking? The microphone output is sampled at a frequency of 5 kilohertz by an analog to digital converter, ADC. The output from ADC is a series of 4 bits. So they are using 4 bit to store the information. The smallest bit represents 1.0 millivolt. Okay, first sample is taken at t equal to 0 because we have to know when it is started. Now we have to use the figure 5.1 to complete figure 5.2. 5.2 is a tabular column. We have to fill the microphone output in millivolt and then ADC output. So we have to do two things. One, look at the graph and what is a microphone output when time is 0.2 and 0.8. Second, we have to convert the data into digital ADC, digital form, I mean binary, 0, 1 or 1, 0, like that. Okay, let's look at the graph. At 0.2 and 0.8, we need the y-axis values. Okay, so we have the y-axis value as 0. For 0.2, it's 8. For 0.8, it's somewhere around 5.6. Okay, each block is 0.4. So the value is 8 and 5.8. Yeah, oh, sorry, 5.8. Yes, okay. Now it's a 4 bit, so 8 means 1000 conversion, and 5.8 means actually 5.8. I'm not sure whether they took 5.8 because in binary, if we have to add dot, then we will have binary dot also, but that's out of syllabus, out of our focus. So I'm going to write this for 6, 1010. Yep, and also, yes, I checked the marking scheme, 1010 is the answer. Yep, okay. Let's move to the next question. Oh, small portion is cut. Okay, after transmission to the signal, it's converted back into analog signal. Oh my god. So the signal is again converted into analog signal using a DAC, digital analog converter. So what we have to do, using data from figure 5.1 from the previous graph, we have to figure 5.3, the output level from DAC for the transmitted signal from t equal to 0 to t equal to 1.2 milliseconds. So we have to write the digital signal. Now how do we write the digital signal? We have to refer the analog signal but we cannot have smooth transitions of curves. That's the difference between analog and digital. So what we have to do, if there is a curve, then you have to take a right turn, right angle, okay, 90 degrees, something like that. Okay, let's draw this. This is how it will look like. How do I know now? Because okay, let's compare the previous analog signal they gave. Can you see that the highs and lows are matched, but the curve bendings are not matched? Okay, this is the answer. Yes, we have to make sure that increase has to be shown. If the increase is not high, then it's a flat line. That's all. That's the idea. Okay, let's move to the next question. It is usual in modern telecommunication system for the ADC and DAC to have more than 4 bits in each sample. Why? Okay, the more bit we have means if we look at the previous answer, we have less steps. Okay, if we have more bits, then we can have more small steps. High number of steps, but every step is small. Okay, so this is the only reason that they have smaller step. So if more smaller step means even smaller change from smaller change in the analog signal can be recorded. See, the more bit you have, you can reduce the window of recording the change. That's the idea. So how we can put it into answer? Smaller step can be obtained. Smaller changes from input signal also can be processed, stored, or reproduced. You can just write any one word, then you get 1 mark. Ta-da! Yep. Let's look at the next question. Oh, we have one more point. Oh yes, more smaller step means more accurate reproduction. Actually, only 2 points, so you can write any 2, you get the full mark. Okay, let's move to the next question. Okay, nice question from electric field. For any point outside a spherical conductor, the charge on the sphere may be considered to act as a point charge at center. By reference to electric field lines, explain this. Okay. So what they are telling is, we have to consider, or why it is to be considered as a point charge in center. Because electrical field lines are radial. Why it is radial? The naturally available charge, plus or minus proton or electron, is spherical. So the charge, the field will be radial. This is the reason. Okay. So how this field lines? So they appear, either they are originated from the center or they are converged in the center. So in this case, we can just write originated. It's enough. 2 points, 2 mark. Okay, let's move to the B question. An isolated spherical conductor has charge Q shown in figure 6.1. Okay, we have Q, and then we have one more point P. I think there will be some question. Yeah, I know that there is question asked regarding the P, and the distance between P and Q's center is X. Okay, let's move to the picture. Point, okay. Point P is a movable point that at any one time, distance is x. The variation with distance x of the electric potential V at point P. So if we change the P, then there is variation in electric potential V at point P, because it depends on the distance by Q1, Q2 by R, 1 by 4 pi epsilon naught, right? Okay, the recorded value is given in the graph. Okay, it's a nice graph. What we see here, okay, there is a straight line until 2.4, and then it's keep on decreasing until 12. Okay, nice. X-axis we have x in centimeter, y-axis we have volt in 10 power 3 volt. Okay, nice. Let's see what question they are asking. In the next page, use figure 6.2 to determine the electric field strength E at point P when x is 6 centimeter. Okay, this we can do it in two types. One, we can use formula, more accurate method, or this one, let's see. Okay, so what do we have here? We have to find the gradient at the distance that they have asked, nearly 6. So I'm trying to find the gradient here. You know how to find the gradient, y2 minus y1 divided by x2 minus x1. So if I get the value from the graph and then I put it in the formula, what I get is 9.5 into 10 power 4 volt meter inverse. Okay, these are the 2 points. I get gradient. Okay, but problem is, so this is a line continuously changing. Which point, and we are not computer to draw the perfect tangent or slope, so line, so that we can find the slope. Okay, so we have to, it's better to use a theoretical method. Okay, so what's given, when x is 6 centimeter, the voltage is 5.4 into 10 power 3 volt. Now this is a formula that we know. V is q divided by 4 pi epsilon naught into x. X is the distance. What is E? Okay, by the way, we need E. We know that V is this and we know E is this. So can we replace, instead of this q by 4 pi epsilon naught x square in the E, just write that x square as x dot x. Okay, so keep the 1 divided by x separately. The remaining, all the remaining things are V. Okay, so what we can write it as E equal to V divided by x. That's all. We know the V, we know the x. If you put there, then we get the answer. 9 into 10 power 4 volt meter inverse. And what we have is accurate answer. Actually, the answer we found from the graph is precise, but it's not accurate, at least according to the marking scheme. Okay, yes, it's 9.0 into 10 power 4. How volt by meter change into Newton per coulomb is an interesting story. I'll let you find yourself. It's very simple. Just try to define what is 1 coulomb. Yep. Okay, let's move to the next question. Yeah, it's here. The radius r of the sphere. We have to find what is the radius r of the sphere. Okay, let's look at the graph. Okay, now we can see that there is a straight line, horizontal line with 0 slope. Why it is 0 slope? If you wonder, then you know the radius, because inside the conductor it is 0. That's all. The change, the potential, and that is radius. So if you measure that guy, you can directly write in the answer 2.5 centimeter. That's all, as simple as it is. But if you are wondering how to explain, if they ask reason, then electric field strength inside a conductor is 0. So in the graph, until 2.5 centimeter, the gradient is 0. We know that the gradient is electric field strength. So the radius is 2 centimeter. That's all, 2.5 centimeter. Yep. Okay, let's move to the next question. Okay, I know that this person is not now not still there with AS and A level physics, but still the purpose here is learning also, not only to score. So we can simply just go through the question. What is mean by feedback? Feedback is naive answer is just take one output and then put it into the input. That's all. So definition is part of output is given to the input for a reference or a potential or voltage, whatever signal. Okay. What is the benefit? For example, in general, what is feedback? After doing a presentation or some work, we will ask friends how was that? Why we are asking? Because if they are giving some suggestion, next presentation we will improve. That's the same idea. Feedback increases the operating stability, increases range or frequency. So actually I don't want to explain this in detail. Okay, if you have if the person is not skipped, I would have spent more time on this, no problem. Okay, now same, let's just start at output stabilizes the grain. So you can just write anything, then you get the answer. Now let's look at the B question, amplifier Okay, we have a circuit, we have operational amplifier, we have plus minus 5 volt on both side. We have a AC signal, there is voltage out there. We have one known resistor and one unknown resistor. Probably they are going to ask what is the resistance of unknown resistor, and everything is grounded below. Let's see what they are asking. When the potential at point is 48 millivolt, the output potential difference is 3.6 volt. Determine first the gain of the amplifier circuit. So gain is simply output by input. That's all. Answer is there. Okay, but what we have to careful about here is it's given as millivolt, so we have to convert into volt, standard SI. Okay. Now the resistor of R, resistance of R, that we have to find. Okay, there is a formula. This gain is 1 plus R feedback, resistance of feedback divided by resistance of input. So the resistance of feedback is 9.92.5, that's given in the picture, one known resistor. Okay, so I have rewrote this equation for Ri, input resistor. So the gain minus 1 moved here in the denominator. So if we put the value, then we get answer. Nice. Okay, so the answer what we get is R equal to 1.25 into 10 power 3 ohm. Okay, the answer is only asked in ohm. So what we have to do, we can write either 1.25 into 10 power 3 or 1250. Yes. Okay, now second question. In third part, second question. State and explain the effect on the amplifier output when the potential at P exceeds 68 milliwatt. Why particularly 68 milliwatt, if you are wondering? So that's our maximum gain. Okay, now what we can write simply, output is greater than input, so it will saturate. The output voltage will be 5 throughout, that's all. Yep, bye bye old syllabus. Okay, now we have syllabus. Coming back to the track. A thin slice of conducting material is placed normal to a uniform magnetic field, as shown in the figure. Okay, now let's imagine that it's our mobile phone placed on the table. So current is how we will charge, in the direction current is flowing. Okay, so magnetic field is how we will touch the phone, mobile phone for touch screen, in the direction magnetic field is going. So this is given information in the figure. Let's see what they are asking. Okay, they are explaining magnetic field is normal to CD, EF, blah 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 blah, what I have explained in simple terms. First question. Okay, a potential difference, the Hall voltage is developed across the slice. State the phases between which the Hall voltage is developed. Okay, now we have to use hand law, left hand or right hand. I'll let you to choose yourself. Okay, now magnetic field and current is perpendicular, they cover two axes. The Hall voltage will be developed in the third axis. Okay, so in this direction. So what is his phase? DERQ and CFSP. So in these two phases only the Hall voltage will be developed. Next question. Explain why constant voltage VH is developed between the phases you have named in one. Why? Okay. Then we have to explain the story again inward. Current is flowing in the direction of QR. So charge carriers are moving in that direction. Okay. So they are moving with relevant to the magnetic field, perpendicular. Then the charge carriers experience a force perpendicular to the current and magnetic field, because themselves they will create something and they will oppose everything. These three guys will oppose each other at 90 degrees. Okay, and because of this potential difference builds builds up across the material of slice, where you can develop potential differences only the third axis. Okay. Now once the magnetic field, already one magnetic field is applied here, is if that magnetic field force is equal to the electric field force, then there will be no Hall voltage. That one point we can add. So we have 4 marks. Yep, let's move to next page. Two slices have similar dimensions. One slice is made up of a metal and other slice is made up of a semiconductor material. For the same values of magnetic flux density and current, state which slice, if either, will give rise to the Hall voltage. So which will be higher, they are asking. So the critical information here is one is metal, another one is semiconductor. So we have to know how many electrons will be there in electron, in the sense charge carrier in the semiconductor, how many will be in the metal, and how Hall voltage is related to the number of this electron or charge carriers. Why we are mentioning electron and charge carriers? Because these are the difference between metal and a semiconductor. Okay. Now the Hall voltage is inversely proportional to the charge carrier number density. We know this equation, VH is inversely proportional to rho. So the higher the carrier, lower the Hall voltage. So who has higher carrier? Metal. So they will have the lower Hall voltage. So semiconductor will high. So that's a point, 2.2 mark. Yep. Okay, let's flip the page, next page. State what is mean by field of force. Weird, very weird. Okay, field is a region if you enter where you experience a force. That's the answer. I'm not going to blabber this more. Okay, now we have a B question here. Explain the use of uniform magnetic field and uniform electric field for the selection of the velocity of charged particles. You may draw a diagram if you wish. Now this is a trap. They will tell you may draw a diagram if you wish, even in paper 5 and ATP in IGCSE. But if you don't draw the diagram, I don't know about other, but particularly I will think, okay, this guy don't know. He does not know anything like that. Okay, why to bother? Let's draw a diagram. Let's assume that we have electric field in this direction. We have the particle which we want to measure the velocity, and then perpendicular to the electric field we have magnetic field horizontal. Okay, let's assume that the velocity of particle is going from left to right. So how we will measure? Basically they hate each other. Electric field and magnetic field, they are perpendicular to each other. Now the velocity, in which direction it is? It is perpendicular to both. So the particle will experience force because of magnetic field, also because of electric field. So what is the force because of magnetic field is BQV, we know that. What is the force because of electric field is QE. From this, if you cancel out Q and Q, we will get velocity is E by B. And why we said in the earlier case, if for example if electric field and magnetic field is same, then V is 1. See, from the proportional you get the idea. Yep, let's move to the next question. Okay, see, they are asking, okay, beam of charged particles enter a region uniform magnetic field and electric field, same, repeat, blah blah blah. Now region of uniform magnetic field is like in the table plane. Okay, so perpendicular to this we have electric field. Now what they are asking, the direction of the magnetic field is into the plane. The velocity of charged particle is normal to the magnetic field as particle enter the field. Nice. A particle in the beam has mass m, charge plus q and velocity v. The particle passes undeviated through the region of two fields. If it has velocity v and charge plus q, it passes through undeviated. Okay. Now sketch the path of a particle that has same mass but charge 2q and velocity v, same velocity. We have to mark this as q, and same mass but plus q, velocity larger than v. Okay, what do you think, which will affect? Yes, obviously mass and charge is not going to affect because we will cancel out like what we have seen in the equation. What will affect is velocity. Okay, so the first one will not deviate because this velocity is equal to E divided by B. Okay, but the second one, they have slightly higher velocity, so they will deviate. Let's see how to draw this. So first one has mass m and q plus 2q. It's q, it will go undeviated. Second one, mass m and plus 2q, has slighter high velocity. That's why the line went a little fast. We have to mark this as a v. Yep. Okay, let's move to next question. Question number 10. Flip. A metal surface is illuminated with light of a single wavelength. Okay, we are talking about photoelectric effect. Sketch the variation with lambda of the maximum kinetic energy E max of the electrons emitted from the surface. Okay, so this is a slightly twisted question because what we learn in the syllabus, syllabus it's there, but in the book, both in Hooder Education and Cambridge recognized textbook, frequency versus lambda, frequency versus energy is given. So now they are asking energy versus lambda. Okay, on your graph with symbol lambda naught, the threshold. First we have to mark the threshold wavelength. Okay, let's take this point as a threshold wavelength. And then how we can find, what do we know any equation to draw? Yes, we know. So E equal to h nu, this we know. What is nu if you ask? It's c by lambda. So this is the equation you get. E equal to h c by lambda. C is the velocity of light here, h is Planck constant, and lambda is wavelength. Now, what is this EP, potential? This guy is work function plus K. Work function a little complicated. What is work function? If you're wondering, we have to slightly deviate from paper solving and then enter into quantum mechanics. So I'm not going to do that. Obviously, we'll do in some other video. Yes. Now, plus kinetic energy. Okay. So now the graph will look like this. Okay. Why it is increasing from this direction? Because only from threshold, only if it decrease below the lambda, then the energy will increase. That's why. Okay, if you are drawing for energy max versus frequency, then this will be opposite because we know that frequency is 1 divided by lambda. Yep. Okay, let's move to question B. A neutron is moving in a straight line with momentum p. The de Broglie wavelength associated with this neutron is lambda. Sketch the variation with momentum p of the de Broglie wavelength lambda. We can use the same equation, lambda equal to hp, different version. Okay, from here what is h? Lambda divided by p. Now we can see that one guy is constant here, lambda is constant, so h is inversely proportional to p. So how you will draw, for example, y equal to 1 by x, the same equation. This is the line. We should be careful that neither of the end should never touch the axis, because y equal to 1 by x, they don't touch the axis. They touch when it's 0, but here it's not going to be 0, so they don't touch. Okay. Yes, let's move to the next question. Okay, next question. 11. The circuit of a full wave rectifier using 4 ideal diodes is shown in figure 11.1. Okay, there is input, there are 4 diodes, there are 2 point A and B, and one resistor R. Let's read what they are saying. Resistor R is connected across the output AB of the rectifier. Okay, another resistor. Same resistor. On figure 11.1, draw a circle around any diodes that conduct when the terminal X of the input is positive with respect to terminal Y. Okay, so X is positive and Y is negative. How the current will flow? So actually there I saw one nice video, maybe I'll put it in the description link. You can see how electricity is conducted through full wave rectifier. Okay, let's go back to diagram and do this. If x is positive, obviously the current is not going through the line, it will be going the base of the triangle side. So this side, and then from the negative, it will not go from the base, it will go from the line. So this side. So negative and positive. For the both questions we have answered. Okay, actually we didn't read the second question. Label positive and negative terminals from the output AB, of the output AB. That's all. We have marked both. Nice. Okay, but the next page, the variation with time t of the potential difference V across the input xy is given by expression V equal to 5.6 sine 380t. So whenever we see this kind of equation, then you can directly compare to y equal to a sine omega t. So omega is 380, V is y amplitude, 5.6 is amplitude, V is y output. Okay, the variation V is measured in volts and t is measured in seconds. Let's okay. Now we take a good look at the graph. X-axis is time, y-axis is rectified potential difference in volt. Okay, this is a full wave rectifier, so it will turn the other half going down into upside. So what we will have consecutive mountains. Yep, let's go to, let's see the detail. What's the question they are asking? Next page. The number of times per second that the rectified potential difference at the output reaches a peak value. Number of times per second that we have to find. Okay, how do we find? What we have to do, we know that omega is 2 pi f. Okay, compare this into the equation V equal to 5.6 sine 380 t. Okay, in this directly we can tell omega is 380. So we can compare this omega 380 equal to 2 pi f. So from here what is f? 380 divided by 2 pi, and you get the direct answer 60.47 hertz. Now we know the frequency. Number is 2 times frequency. Why? Because frequency is for one cycle going up and down, one full cycle. But what we have done is full wave rectifier. So we cut the down part and then put it up again. So now the number is 2 times this frequency. That's why we are multiplying by 2. So if you multiply by 2, then we get 120.95. That's the answer. Let's see what more they are asking. Okay, see, a capacitor is now connected between the terminals A, B of the output. Okay, the capacitor reduces the variation in the output to 1.6 volt. So two information, one connected capacitor, and then the capacitor reduces the variation by 1.6 volt. First question, on the figure 11.2, sketch the variation with time t of the smoothed output voltage for the time t equal to t1 to t equal to t2. By the way, connecting capacitor is called smoothing, that we already know. So what is going to happen here? So instead of the wave from okay, I'll point it. The wave, for example, it's increasing from 4 to 6, again it goes to 0. But if we connect capacitor, it will store some energy and it will connect to the next. So it will go like this. Instead of going straight down to the 0, it will just go like this. This is the idea, connecting capacitor. This is called smoothing. Nice. Second, suggest and explain the effect, if any, on the mean power dissipation in resistor R when the capacitor is connected between terminals A, B. So what will happen? The energy is stored now. So the mean potential difference will be higher. Okay. Root mean square potential, RMS potential difference is higher. Potential difference is higher. Then what will happen to the mean power? It will decrease. I was kidding. It will increase. Okay. Yes. We get 11 out of 11. Okay. By the way, I am not answering these questions directly by seeing the paper. First, I look at the paper, I refer book, I'll try to solve myself. If I cannot solve, I'll refer the mark scheme and then I'll solve. Yep. So, even if you don't trust me, you can trust the marking scheme. Yep. Let's go to the, I think this is the last question. Okay. The isotope of iodine 13153I is radioactive with a decay constant of 8.6 into 10 power minus 2 by day. Beta particles are emitted with maximum energy of 0.61 MeV, capital MeV. Okay. State what is meant by radioactive. What is radioactive? Emission of electromagnetic radiation from unstable nucleus, and this is spontaneous. 2 points, 2 mark. Spontaneous emission of electromagnetic radiation from unstable nucleus. Second, what is decay constant? So here we will use the symbol lambda for decay constant in nuclear physics. Yes, it's a probability per unit time of the decay. What is the probability? How many times the nucleus undergo decay? By second or by hour or by day, it depends on us. So the definition is decay constant lambda is the probability per unit time of the decay of the nucleus. Yep. Okay. Let's check question B. Explain why the emitted beta particles have a range of energy. Why? Because beta negative particle never comes alone, or never created alone, or never emitted alone. They always emitted with other particles. So they share energy with other particles. Okay. And so literally, I'm not sure. Please check yourself. Literally, this beta is considered to be electron, but these are not normal electrons outside living in the orbitals. Okay, these are proton or neutron. They are converted to electron after emitting some particles or some energy levels. So what are these particles called? Neutrinos or antineutrinos. Yes. Okay. Yep. Let's look at the question C. A sample of blood contains 1.2 into 10 power minus 9 gram of iodine 131. Determine for the sample of blood the activity of the iodine 131. Now what are the information we have? First we have to find the lambda. Okay. So lambda is from the, we can refer the initial value. Yes. Lambda is 8.6 into 10 power minus 2 by day. This day we have to convert into seconds. That's what we have to do. And we have energy 0.61 MeV. Okay. Our remaining is there. Yes. So lambda is 8.6 into 10 power minus 2 divided by 24 into 60 into 60. 60 for minute, 60 for second. So it is 9.95 into 10 power minus 7 second inverse. Okay. Now we know the formula. Activity A is lambda divided by n. But what is n? Is n given in the question? Now we have to find ourselves. N is mass divided by mass number multiplied by Avogadro constant. Simply mass multiplied by. So you are just dealing with mole divided by mass number. That's all. Mass multiplied by Avogadro constant by mass number. So if I do this, mass is 1.2 into 10 power minus 9. It's already given. Mass number is 131. Multiplied by Avogadro number is 6 into 10 power 23. Answer is 5.5. If you do the calculation, use the calculator or do mental math. 5.514 into 10 power 12. By the way, if somebody is wondering how these units of lambda, and Avogadro number get, just place the unit and do the dimensional analysis. It will be very easy and interesting. Yep. Okay. Now activity A is n divided by lambda. We have the lambda found, we have the A found. The answer is 5.486 into 10 power 6 becquerel. Becquerel is given already there, so we have to write only 5.486 into 10 power 6. Okay, do we have one more? Yes, okay, we have one more part. In the time for the activity of the iodine 131, the time for the activity of the iodine 131 to be reduced 1/5 of the activity calculated in 1. Okay, now we are talking about ratio. This also we have the established formula in book. N divided by n naught equal to e power minus lambda t. I want the t. So what I am going to do, I am going to take log base e. People call it as ln, but it's log base e of n. This side, if I take both side, if I take log, na, that side log e is simply log e power x is x. Okay, so here I want only t, so I am rewriting this equation, putting lambda divided on the other side. Okay, now we know all the information. 1/5 n divided by n naught is 1/5 divided by minus 0.086. This is t. How much is t? 45.48 days. Okay, how it is days, let you find yourself. Okay, why it is not in seconds. Yep. Okay, let's look at the next question. Oops. Okay, question is done. Thank you very much. Let's see in the next question.